Well, it's been several months since my last cast of my latest circuit designs. Of course, you may or may not know that my YouTube channel by the name of Vinyasi was taken down around the time of my birthday. Um, it was under attack before. This wasn't the first time. But this time, the attack was quite um, dynamic. um, I had thousands of videos, thousands of subscribers. Now I have more than one channel, but that was the one with my name on it. And if you're wondering what happened to it, it just, when you have an opinionated person of varied interests, it's very easy to come under attack to, anger someone. And I'm pretty sure it was a cozy relationship between one of the YouTube administrators, at least one, and at least one person outside of YouTube to do the flagging, and then the administrator to authorize the taking down of that video. And all you need is 3 flags, 3 hits in a 3-month period, and then the whole channel goes down. And if it goes further, then the whole account goes down and all the channels with it. So I stopped posting to YouTube. Unfortunately, YouTube, and you see, before we lose this, you see the voltage is dropping. I just turned on the circuit without activating any of its elements, and so it's showing 0 volts, 0 amps on the inductor over here, and it's a 100 nanosecond time step and a very slow, moderately slow simulation speed, very slow current speed. And so whatever voltage is entering through the aerials, it's energizing the system here. You can see the little yellow dots, but it is diminishing because of the various internal resistances, the resistance of the coils on the transformers, and the resistance, not much to speak of in the capacitors. Good deal of resistance over here, 1 peta ohm, which is 1,000 times of a tera, which is 1,000,000 times of a giga, and 1,000,000,000 times of a mega, 1,000,000,000,000 times of a kilo ohm, or 1 quadrillion ohms, basically, is 1 peta. Shorting out the 2 aerials, such as it is, each of the transformers has 10 henries on them. 1-to-1 relationship. No. Oh, I'm sorry. This has to be redrawn. No, they're 10 to 1, 1 to 10. So the primary on the left-hand side is 1/10 of the voltage on the right-hand side. So all the voltage gets piled up by the aerial, and all the current gets piled up by the load. And that's pretty good. It economizes where to put the current. We want it on the load, and not on the aerial, because we want to keep the FCC happy and not produce radio interference in our local vicinity too readily. But you can always safeguard that by making your aerials the inside of hollow metallic spheres, such as bronze spheres, so that it doesn't broadcast to the outside world. Or you can use flat surfaces and blow compressed air or wind across those surfaces. I'm not sure about the hollow spheres idea, but it's something Earl Aman has done. He took out the headlights of his car and put in bronze spheres, and I suspect those were 2 aerials. With a 2 aerial system, it works pretty good. You just have to make sure you create a phase difference between the 2 aerials, either by having a capacitor in series with one of them, or both of them, but of differing values. And I made these extremely different, 1 farad here and 1 picofarad here. And that'll create a phase relation difference between these 2 inputs, even though the input is otherwise the same. Before it reaches the aerial, the radio waves, we assume, are the same, although they'll be hitting these two aerials at two different times in real life, but here in the simulator it hits them exactly the same. So we may not need two different capacitors here in real life, because there will be a phase time difference, a phase times difference between the two antennas receiving the signals from outside. But just, for the case of the simulator, I had to put these in. Now, it looks like these are all broken circuits here, but it's not true. These are analog switches which are connected all the time. It's just a question of how much resistance is in place when the circuit is closed versus open, when the analog switch is closed versus open. I keep them in the open position because, interestingly enough, in this circuit design, resistance is to our advantage. It actually exhibits the behavior of negative resistance rather than positive resistance. That's why I use such a big resistor here, because it helps. When these analog switches are open, there's 20 gigaohms of resistance, as opposed to when the switch is closed, it's, 10. Let's read it off. Here we go. 10 gigaohms of resistance when off, 20 ohms of resistance when on. So it's to my advantage to put in these analog switches and then freeze them with 2.5 volts in the open position, except for this one, which is a short that I use for creating a closed loop here to run this inductive load. Now, all of these are daisy-chained LMD modules in longitudinal magneto-dielectric mode, because they're daisy-chained using the coils as shunts, namely the magnetic core of the transformer pairing of coils as a magnetic shunt. Isolating each of these 5 LMD modules and isolating the aerials and isolating the inductive load. But it's all oscillatory. It's all, it alternates in direction. That's the nature of the LMD module. And, emulating a transmission line, in this case, emulating it cross-sectionally at a perpendicular to the length of the transmission line, namely across the space between the two wires. But because they're 5 daisy-chained, it's more or less kind of like 5 pairings of transmission wires. And we're going across the space between each wire to the next wire. And that's what across, I mean across in terms of the series along here. When we hit the dielectric of each pairing of capacitors, it's like the airspace between the two wires. And the magnetic core of the transformer in the simulator is like the magnetic field between any two wires, or the magnetic field within each wire, actually, surrounding each wire. But I do a lot of isolating here. Anyway, so I put a diode here to convert all of these oscillatory waves, these alternating current waves. As you can see, they alternate, but they alternate so fast, the cycle time, that it gets a wash of color, green for voltage, yellow for amperage. But these are actually compressed sine waves that are going in the positive and negative equally so. But in this case, due to thermodynamic losses, it's inverted. It's a diminishing Gabriel's trumpet. Look that up on Wikipedia. But at the last minute, I put in a diode to convert all these these oscillatory alternations into direct current, because I want this to be a DC output. So I got 10 henries on the coils, 18 farads on the capacitors. But now the capacitors, if you read these instructions, you're supposed to set up the parametric minimums and maximums at 18 versus 27. And so now I set up this one. So the next one I'll do in reverse. I'll set up 27 versus 18. And that's 19, excuse me. 18. Nope. I don't have my glasses on. 18. Now, because of the nature of the software that Paul Fawcett software that I modified, every time you put it in, it flips the other one. Every time you make a change. That's why I have this thing here. Because, see, now I created a shockwave there of current, a surge. So if I do it to enough of these, or to all of them, it should increase power. Right now, it's not increasing power. So I just have to go along and do all of them. So I do 18, followed by 27. But you can see some flickering here, so I must have done something. And then, oh, see, look at that. It's already getting a response. And then 27 versus 18. Okay, so now if we look in the lower right corner there, we have these four are set up. Minimum PE and maximum PE, but they're inverted. Yeah, 18 versus 27 or 27 versus 18. Actually, I'm going to have to stop this. Or else I'm going to get results that will be uncontrollable. Uncontrollably happy results. Alright, so I'm showing you how I go about this because I don't give any help instructions down here like I should on one of these links to help walk you through this. So I just try to do it in my videos instead because I'm lazy. Alright, which one are we at here? Oh, that one, okay. So whatever you do, you just keep alternating how you do it. Whoops, wrong one. Did that one already. Ooh, I did this one too. Oh, okay. 18 over 27, 27 over 18. Okay, so now we move along to this one. And 20. Whoopsie. Little finger happy there. And then we do 27 versus 18. See, so they all line up 18, and that's important. So when we press the switch, they all change at the same rate in the same direction, up or down. In this case, down, up. Okay, 1827. And then 2718. It doesn't take too long to do this. It's just, I wasn't able to change the software to make it something permanent that you could store, you know. Alright, so now we restart the circuit. And now we give it a flick. And we've given it a jolt of energy. See the spike? But it's still not much because it still doesn't register even at Yocto units, which is 10 to the power of negative 24. So we keep doing it a few times. Now we're starting to get 0.13 Yocto volts spike and negative 0.14 Yocto volts here. The amperage still nothing. So we just keep doing it. And what we're doing here is at random is we're going into and out of, see now I held it there for so I got quite a jolt, into resonance and out of resonance of the parametric oscillations of an LMD module. An LMD module automatically, parametrically oscillates. It's by its nature, if you've set it up correctly, if you found its sweet spot, its resonance point zone in which synthesis of electricity occurs. Now, right now, there's neither synthesis nor decomposition. It's just thermodynamic losses due to, well, I'm assuming. I could be wrong. It could be decomposition. How can you tell the difference? Because decomposition and thermodynamic losses, by their nature, macroscopically at any rate, look the same. So how would we know? But I set up a switch here all by itself to act as a changing medium. I mean, you can do anything. You could have a little very, you could have a very tiny resistor. You could have use this resistor and just flick it. See what happens? And it flicks, it changes. But look, I went too high. See, I overshot. So let's stop. And then if you go too high, then the simulator crashes. So let's reset this to the beginning point. But the resetting doesn't clear these, so I still have my settings here, so I can flick this and move my way up, or hold it down a little. And now let's see. Now that's a little high, see? Well, not for milliamps. The milliamps still needs a little bit more of a helping hand there. So this is escalating, or by way of synthesis, the energy. Now I went a little high. So I got kiloamps here. Is that? No, I got megaamps. And this thermodynamic loss, it's cascading downwards. And I have a teravolt spike, but it's really gigavolts if we reset this. That's the spike, but it's... Now this is the stored energy that's being dissipated by way of the various 10 gigaohm resistances in all of these switches. So right now, those 10 gigaohm resistances are acting as thermodynamic losses, running the system down. But when we get into the zone of synthesis, those resistors actually act as negative resistors. So, that's the caveat. It's a push-pull, gain-loss situation. If you can take the resistors out with the right switching, then you'll be even better off. The thing won't diminish so fast. But this is a proof of concept demonstration. I'm trying not to make it too complicated. So we see our inductive load is zipping around in DC format. It's just losing its power fairly quickly. Now I'm not sure if it'll stabilize. We can wait and see if it's stabilized. In the meantime, I'll start talking. So I have a circuit information button here. You can click on it, and you get to read about, the operation of this device, its origin. I don't think I said its origin. No, I did not. I left that out. Sorry. Okay, its origin is a specific circuit. My very first over unity breakthrough on the night of the 17th of March 2017, and I don't want to lose this circuit, so what we'll do is we'll start a new private window. See, if you don't do a new private window, or a new window I should say, then the JavaScript loses the focus and then it stops running. So if you do a new tab, so I do new windows, not a private window, a new window. Okay, so this was my first breakthrough. So we have these daisy-chained modules. Here I only have 3. I have 10 farads, very similar to 18 or 27, and 300 henries, very similar to the 100 henries. I think it's 100 henries. Let's see, let's go check. 10. No, I'm using 10 henries. A minimum amount here, 10 henries. I brought it down a bit. Now, what that does is it increases the... let's go back. It increases... Well, it diminishes impedance. It diminishes the ratio of volts to amps because in a lot of these situations, voltage predominates to an excessive degree. If you're out of this particular zone, which is kind of favorable, and notice I have all my coils in counter wound position. That also helps as a negative resistor. Where was I? If you're not in this particular zone, then the impedance can be very huge, like 10 million, 10 mega ohms, And who wants to go there? You don't want your load to exhibit the extreme voltage, you know, you want it to be reasonable. And so I was able to bring it down to a factor of 20 times more voltage than the amperage. Once it stabilizes. That's what's exhibited on these very slow-moving graphs. So if we go back to this one. So this thing is running, and we got to give it some juice by flicking the switch, if it lets me. There. But it went to infinite gain. And it never used to do that in the regular simulator. Now it does it in the realistic simulator, because all of my resistances within these coils are acting as negative resistance. I put equivalent series resistance within the coils, and also within the capacitors, but it's in the coils that normally that acts as a positive resistor. But when you have LMD chained modules, the resistance of a coil actually acts as a negative resistor. And then you got the resistance of the lamp helping out, you know, all these various resistances, and then you get this infinite gain instantaneously, which I didn't get that on the night of the 25th of February, excuse me, it wasn't March, 25th of February 2017. It was actually a gradual rise. And I'll show you what I mean by using the other simulator, if I can find it here. Is this it? No, here. Okay, remote desktop simulator. So this is the prior simulator that I used to use without equivalent series resistance. And if I can find, here it is. Now we give it a flick. If I can get it. There. So there's a spike, and it's slowly going to escalate. Now if I had closed the switch, it would have escalated more slowly. Because the AC input, the AC source, acts as an anchor weight, preventing the quick increase of energy, as you see occurring right about now. But if I open the switch, it grows more rapidly, slightly. And it looks the same. See, right at moment, for a little bit, it stops the surge, but then it picks up again. But then I open the switch, and it tends to increase the rate slightly. Now this is going to take a while to reach infinite output. Even though I panicked that night, I didn't really know what I was doing. It was the first time I'd ever witnessed over unity in front of my face. But I learned from this experience that Eric Dollard's LMD daisy chain is a surefire guarantee for over unity. All you have to do is daisy chain several modules. Actually, you only need one. It just has to have the right values, and that you just have to tinker with. In this case, I didn't have to make them small, like I used to have to do in my other simulations. I made it very large, and this works well both in equivalent series resistance modality of simulation versus without equivalent series resistance, which shows me that this is a surefire ticket to over unity. So this is still slowly. Maybe we could speed this up. Well, not too much. It kind of gets jumpy. And I am screencasting, so that will slow it down a bit. It's going to take a while to... Well, anyway. So, let's see. What do I have to talk about? See, I talked about the voltage is over on the right and the current is on the left. I talked about the brakes, negative resistance. So I'm going to have to redo... Oh, it's... Yeah, no, I'm going to have to redo this singular text line is not accurate. Little oversight on my part. Because you can see when I open up the edit box that the ratio is 10, which is 1 to 10 actually is what it amounts to being. Let's see, what else can I say without sounding like I'm saying nothing? Well, let's go review the circuit information. Um, oh, this will take you to the larger size image, but I can't go there because I'm not connected to the internet. Actually, I can show it to you. Well, it's just a screenshot, yeah, of the live version underneath. Let's see. Oh, yes, I give reference to Eric Dollard. Well, I give a reference to Noether's theorem, which talks about conservation of energy is predicated on a yardstick of measurement in which time does not vary. You know, in the simulator we can change time, but in real life we can't, or at least that's what we think. And if time should vary, such as time dilation that Einstein talked about, then conservation of energy does not apply anymore. So what happens is, can time actually be manipulatable? I don't think so, but it doesn't matter because for all practical purposes it will appear to have been manipulated. And Eric Dollard gives an analogy which I think is very appropriate, in which he talks about energy generated at the power plant is totally in phase, lockstep in phase with that same energy at its reception point. And it has to be done that way. They do it with a huge bank of capacitors put in series with the transmission line every 100 miles or so. I don't know, it's like 150 miles or 250, I don't know, I forget what it is. It's a huge room filled with capacitors, and it puts the waves in phase lock. It keeps them in phase lock so that it will appear that the energy did not traverse space because it left the power plant and traversed the distance, and when it reaches the consumer, it's in lockstep. The waveform is in lockstep at both points A and B, making it appear as if it didn't travel across any space, because if they hadn't put in those banks of capacitors, the speed of light being a very, rigid limitation, energy takes a certain length of time to travel, and in the course of its travel, the wave at the power plant will not be in phase with the wave at the receiving end. So this is what they did to get things in phase, so that it will look like no space will have been traveled. Well, electricity can do things like that. You can do all kinds of things to it to make it look like we're manipulating time, and so I suspect that's what happens, even though Eric says, explicitly, electricity can travel backwards in time, it can travel forwards in time. I'm beginning to wonder if that's really true. I've never seen it happen. What I have seen happen is things that look like we are breaking the law of conservation of energy, by way of varying time. And so I suspect we're not varying time, we're just doing things that make it look like we're varying time. Now, there's something about the LMD module that's magical, because it literally manipulates parametric oscillations. In other words, it manipulates the parameters of a capacitor and of an inductor, changing them over time to either synthesize or decompose electricity. In this case, you saw me escalate it, and so it was synthesizing. So it does it somehow, I don't know how. Eric, does promote the idea. He has stated as such that caps and coils can synthesize electricity. And this is a simulation that actually shows this, just like my other breakthrough in over Unity over a year ago showed it. So time may not be manipulated, but effectively speaking, time will appear to have been manipulated. I mean, that's my guess. At any rate, the parameters of a capacitor and of a coil can be manipulated, even though we put them in the circuit with fixed values. The only reason why I have an example in the text here of a variac, because to put us in the zone and take us out of the zone, is because I don't want this thing to go to infinity. I want to regulate it. The problem is it shoots up so quickly. 100 nanosecond time frame. We would need sensors and a circuit that responds so quickly that I don't even know if it's possible, quite frankly. So that might be the only caveat to this circuit. Otherwise, the circuit is buildable. And this peta-ohm resistor, you do what you can manage. Whatever you can manage helps, as large as possible. But the coils, although large, are buildable. The capacitors, although large, are purchasable. But the voltages reached in here the spikes can be quite extreme. So that means, that's another caveat, that all of these components have to be proofed for extremely high voltage, far higher than the operating level of voltage that you plan on running it at, because the spikes that you get, the surging spikes in the course of changing into and out of the zone, so to speak, of synthesis of electricity, those spikes can be humongous. So that's, there are a couple of caveats actually to this circuit that might make it prohibitive for anybody to actually build it and test it. But thematically, it looks very reasonable. Nothing really extreme, out of the ordinary. Too much so. I kept the ratio between the primary and the secondary coils on the transformer at a reasonable 10-to-1 ratio. The coupling coefficient is 0.999. Yeah, 3 nines. So we're still coming down here. We've got kiloamps and megavolts. A lot of kiloamps, 925 kiloamps. Let's see what else. Oh. So I kept the henries on the inductors high in order to keep the ratio between the voltage and the amps low. One of the benefits of lowering the henries, the inductance on these coils, is that you get a much quicker response time to the synthesis of electricity. When these 18 farad capacitors leap into 27 farad value. And of course it would be more lightweight transformers, easier to build. What was the other thing I wanted to say? Oh, there was a little problem I had with the simulator, and you may not have to do it. I had to break up these lines here. You see separate lines. It was giving me a wire loop error message, so I had to break it up. Otherwise, I wouldn't have had to have done this, that break. I would have just gone right over and across, like I did here, once, twice, 3 times. But I had to break it up 3 times. Let's see. There might be some leakage of this voltage going into the switch and coming into the power supply. So even though it's only 2.5 volts, if that's true, then this voltage would tend to leak out and overwhelm this voltage supplied to operating these switches. So that's a little unrealistic to assume. If it leaks, can you get away with it? Probably would have to have a diode protection to protect it from leaking outwards, if that's the case. Let's see, there must be a lot to say about this. Well, I did this for a reason. I'll tell you the reason. My car is in terrible condition due to rabbits and rodents chewed up the wires. The wires are fixed. You know, the car's in, I took it to Toyota dealer and they fixed it. Not all dealers will fix a RAV4 EV from 2002, but I found one that would. But there was one snag, and I knew this going into the situation. There are no available batteries, neither brand new nor reconditioned, that can fit the battery pack to replace dead batteries. And I have 9 dead batteries now, because I didn't drive the car for nearly 2 years. It's a pack of 24 batteries, 12 volts each, 95 amp hours each, because it's a very heavy car. And I found out, one thing I learned is that the car actually has 2 motors that kind of feed off each other, was the way it was explained to me. I don't know what that means. But anyway, it requires 2 motors and an elevated voltage coming from a double-sized battery pack because the car is heavy. It's over 3,000 pounds in weight. So you need the extra voltage and 2 motors as opposed to 1 motor to be able to move the car around at a reasonable acceleration. You know, to get on the freeway and accelerate and go up a hill or whatever, to a mountain pass. So I've got 9 dead batteries, and then the remaining 15 batteries are not exactly good batteries. Their voltages are quite low. So I only have 150 volts coming out of the pack when it's fully charged, when I should have at least 240 minimally to prevent the car from shutting down. I think it's 225. I'm not quite sure where it is. Let's say 230. But optimally up around 260, 270, 280, 290, maybe when fully charged 350. You know, that's where the battery pack should be at its voltage level. Well, there's no easy way to try to fix the situation. And so what I did was I went back to, I tried all kinds of scenarios. You know, I was trying to contact people, and nobody wants to touch the car, basically, to do any kind of creative solution. Yeah, certainly not Toyota. They have their hands tied. They have to follow the book, go by the book, so to speak. So I went back to first principles. Why did I buy this car? I bought it because I wanted to motivate myself to try to find a solution to the energy problem, the social problem, regarding the energy problem of electric cars, how they are poorly designed not to be efficient devices such as they could be. And I sought an endeavor to train myself, to informally educate myself on electrodynamic theory. This was 5 years ago in 2013 when I first bought this car. I knew just about nothing. I certainly didn't know anything about electrical theory. And for the first several years, all I did was speculate wildly. And it wasn't until I got on this simulator that I started to think realistically and rationally about electrodynamic theory. Although simplified, idealized in the virtual realm of the simulator, still I've managed to be a bit more reasonable in my presumptions. So what my belief was when I bought the car was that Eric Dollard's LMD module somehow would be involved in my self-discovery of how to improve the situation of the very short range that our electric cars have per charge. Unless you buy a fancy schmancy high-priced car nowadays, you can get one that might last a few hundred miles, but it's still pretty limiting. You know, if you have a few gallons of extra gasoline in your truck or whatever, you could refill your tank en route and go several hundred miles, several hundred miles. So I felt the LMD module had some potential. It was just my intuitive gut feeling. And after over a year of simulating, I've come to the conclusion that I have this knowledge already in my soul from some prior set of incarnations in which I dealt with electrodynamic theory. It was just a question of bringing it out. But the only way to bring it out is because we're dealing with details, or I'm dealing here with details, I needed a simulator to help me bring out the memory that I have somewhere in my soul. Because these details, you can't just get them, you know. I mean, I don't know. I couldn't. Unless I get involved with details, I cannot evoke details from my soul memory. All I'll get is just this, vague hunches, like I got the vague hunch that the LMD module would prove productive, and it has. So I've come back full circle. All these simulations, you know, all of the different circuits that I've amassed over, you know, the many months of working on this over, you know, over a year's time, I've come full circle back to his LMD daisy chain, because that is the simplest concept that works the best and is the easiest to at least consider the possibility of building it. What else? Well, you know, I've tried this before, this concept, but it didn't work because I didn't use a double source, you know, like I do here. I learned this since then, and then I figured out to offset it, to offset the phase relation, to get it to work, to ensure that it works. Let's see, so what did so I brought that up because quite possibly the only solution to fixing my car is to ignore the problem, as if the batteries are no longer there. Because we don't need a battery pack, just, you know, the normal battery under the hood to operate the radio and the headlights, because that'll supply voltage to operate the switching, you know, these switching devices here. But I'm using the air, the atmosphere, as my voltage source to energize the circuit. And then I'm using parametric oscillations of the LMD module to escalate the energy that the minuscule energy that I got from the aerials, because there's hardly anything in an aerial worth, you know, making a big deal about. But it's enough to charge the circuit. I could have used a battery to charge the circuit, but I needed these to be offset. I needed a voltage difference between them. Yeah, I could have used a battery and just two different voltages fed into each of these inlets, but I chose not to do that. So, you know, how you do it is up to you. But there does have to be a voltage difference between these two inlets, but it can be really minuscule. This was actually a lot, 20-volt waves, you know. If we scope this, you can see that it's a 20-volt wave. Well, actually, this wave is not 20 volts. It's more like 5 volts for some reason. Probably because I have the capacitor blocking it, and I have it shorted with this resistor. And then if we look at this one, we can see that they both have the same voltage level, but they should be out of phase with each other slightly. Let's see if we stack them. Where does it say stack? Oh, that didn't work. I want to stack them all. And then I want to unstack this one. Well, that didn't help. Oh well, whatever. Here, why don't I just take out that wave? Remove that scope. Yeah, let's remove both of these, since it's not getting me anywhere. Restack it. And then move it up. Alright, so did I get these moved? Well, the peak of this is 93.79 milliseconds. .8 milliseconds. Yeah, so this wave, the voltage leads this wave by 10 microseconds, which is all it really takes, you know, to get a phase difference between the two waves. Now I have to remove those scopes. let's see what we're really looking at. We're looking at the inductor. So we got kiloamps, and they're coming down, and megavolts. Let's see if I covered everything. I guess I have. There's nothing more to say. Okay. Well, yeah. So I guess you could say I'm hopeful, although I may be dreaming, to build something like this, or employ somebody to build something like this for my car, to feed into on top of the motor pack, to add voltage to the diminished voltage that my battery pack is supplying to the motors, to the dual motors, and they will increasingly die and output less and less voltage over time. It's just because, I don't drive the car regularly, and that's a big... Well, now I don't drive it at all, so the remaining batteries are probably going to continue to deteriorate. Oh, I have this at 100 nanoseconds because I had convergence problems. It's one of the issues with simulators. If you get convergence errors, then one way around that is to simply reduce your time step, so that the simulator has a chance to catch up to all the changes, the complicated changes that you're inducing in your fancy-schmancy circuit that's out of the ordinary. These simulators are not built for over-unity simulations. Part of the problem is they're not equipped to handle it, and I'm not running a supercomputer as well. So those two factors, probably the latter is the more likely. But also the simulations, the simulating software is not designed for anything other than AC or DC, I mean, random unidirectional spikes that can spike to very large absolute magnitudes can really tax a simulator's ability to do the number crunching in real time, which is the case in Paul Falstad's simulator. A minor caveat, I guess. I work around it. I try to create circuits that won't have that problem. So that means they have to be simple, not too complicated. Obviously, in the real world, the circuit would be built up and made more complicated in order to accommodate all the fine tuning of the circuit in real life. But a simulator can't handle. It just chokes on it. It just can't handle the complications. So I keep my diodes limited, and I keep my number of elements limited if it gets too complicated, because over unity is a complicated activity. It's extremely complicated for all these calculations to produce results. It's just expecting too much of the simulator, really. So you can either reduce the simulator speed, that usually helps too. You can reduce the time step, and try to reduce the complexity of the circuit. Another thing you can do is locate your simulator on your hard drive as close to the root of your hard drive as possible, because the longer this address becomes in the browser, the more time it takes for every single change to occur in the simulator. For some reason, it has to scan this from left to right each time it makes a change in the simulator. Even if it's not running, if I turn this off, the simulator's still running. See how it lights up? Because so it has to be on its toes, so to speak, running all the time, eager to please me, to light up all these things. Just as one example, You know, the only thing not running is the simulation, but the simulator itself is still running. And every time it responds to any kind of change, it seemingly, from my presumptive thinking, guess estimating, it has to read through the entire URL from left to right, and the longer it is, the more time drag, you know, it drags down the operation of the simulator. So that's why I try to make short URLs for remote locations, you know, and also short URLs on the desktop for my local, you know, implementation of the simulator. Trying to make them nice and short, not very long, and that helps speed up the rate at which the simulator can function, and with less jumps and skips and spurts and stops. We want smooth driving of the simulator. I guess that's it. I've covered just about everything. I highly recommend Energetic Forum because that's a great place to get ideas, and you know, the videos of Eric Dollard and any of the written material that you can get your hands on, because those are probably, for me anyway, they've been the best source of inspiration to work from. In a nutshell, basically. You know, other people are good too. A lot of them, they're all good, but you know, even the people who posted in Energetic Forum, you know, great, very knowledgeable people. But those three are the easiest off the top of my head to recall. Are the best ways to inspire creative thinking in a very good direction. And a simulator helps too. You know, if you're not building things, either way, you know, you either simulate or you build, or both, to get your feet wet, so to speak. I can only simulate. I'm not allowed. My conscience doesn't permit me to build anything, frankly, because I don't know about safety procedures. And the funny thing is, my conscience keeps coming up with, it's not necessary for me to build anything. And it might be true. You know, I may never fix my car. I bought it to motivate me, but that might have been the price I paid. You know, all the money I've put into it, and now it's sitting there incapable of being driven. You know, maybe it's served its purpose. It got me to this point to motivate me, so that I no longer live vicariously in the car driving it around, you know, vicariously interested in electrical, you know, usage in our devices, but instead I'm living vicariously through the life of the simulator. So it's vicarious either way, because, well, except unless you get into bionic circuits, you know, it's pretty much vicarious pleasure. But whatever. Now, there's no easy way to get this energy out of here. I wish there was. That's one of the problems. Another caveat I've had to free energy is that once you create a bundle of energy, you're kind of stuck with it, and it takes forever for it to wind down. Now, this is 100 nanosecond time step, so obviously in real time it would wear down much more quickly. So that's not really a caveat. Just in the realm of the simulator, it becomes a problem. Let's see, anything else I can think of? No, so I hope you enjoyed this video, and now I'll prepare it for posting on Vimeo. Oh, a little something about where I'm now posting videos. So I don't post on YouTube. I post on Vimeo. YouTube videos have a cozy relationship, YouTube, with Google, such that just about anything posted, you know, publicly on YouTube will immediately show up in a Google search, while Vimeo will never show up. So it kind of tells you, you know, who's sleeping with who, so to speak. But at least Vimeo is still useful, you know, because I can use it to link to it, you know, like in social media, like, you know, I can promote it, my Vimeo videos on Facebook, for instance, or on my websites, and not have to host the video itself. So Vimeo is useful. You do have to pay for it if you want to do any extensive uploading. It doesn't come free, which means it's not at the beck and call of advertisers. You know, advertisers pretty much rule YouTube. At one source of rulership, community rulership. So this way I get to, you know, it's my account on Vimeo, so it's not like it's subject to other people's whimsy, or not whimsy, but whatever. It's not up to other people to decide. Yeah, I'll have to post this on my Tesla Pierce Arrow 1931.info website. I haven't gotten to that point yet. I'm still just working on stuff here. Okay, so that does it. So, I hope you enjoyed the video. Now, the image that would have appeared here is my PayPal donate to me image. So if you want to give me money, feel free to click on the image here, the PayPal image that you'll see when you bring this up. The shortcut to this is is.gd/5 LMDs. You know, is.gd/FIVE LMDS. Nice little shortcut.